In this video, we're going to start discussing fluid flow. Up until now, when we've discussed fluids, we've really talked about fluids that were stationary or static was the word we used. But from our real life, we know that really fluids are constantly flowing, whether it's the water out of the tap or the blood through our veins. And so investigating the dynamics of those is going to be really, really helpful for us to understand some of the important aspects of fluids. The first things first, when talking about fluids, we're going to use this term a lot. Capital Q we call the flow rate, and it's equal to V, or volume, over time. This is volume. And so really all it means is just what is the amount of fluid that is flowing through the pipe or vessel or artery or whatever it is. It's the volume of the fluid that's flowing through that pipe divided by the time through which it takes that volume to get through some amount of pipe. Okay, so the units, I'll put these square brackets to indicate the units of fluid flow. We will use meters cubed per second, or we might use centimeters cubed per second. And sometimes, not as common for us, but it's pretty common in sort of everyday life to use liters per second. Okay? But anyway, you can deal more with the conversions later. But the idea, when we talk about flow rate, really all we mean is just the amount of fluid that is flowing through a given part of the pipe, through a given part of a pipe in a given amount of time. Okay, one important thing to point out, and then after we do this, we'll see an example of what we mean by flow rate. But an important thing to point out is that we are going to study what we call incompressible fluids. And so the idea of incompressible fluid is just that if you've got some fluid, you can't squish it and make it a more dense fluid. Our fluids are always going to really have the same density. So let me just make that note. Our fluids will have a constant density. Okay, so nice. And this is going to be really helpful in really analyzing and understanding some of these fluids. Okay, so to get more at this flow rate, let's look at an example of something that you might have encountered before, maybe not, but certainly when I was a kid I did this kind of thing. So let's just imagine that we've got a garden hose. All right, now this could be any pipe or anything that's got water flowing through it. And so the blue is meant to symbolize the water. And let's say that it's flowing at this rate Q. So the idea is that Q is just the amount of water that is flowing through the hose. Let's look particularly at the end. So this is kind of the nozzle at the end, or the end of the tube, whatever it is. And so this water would flow. It would come up here and flow out like this, and boy, it would just kind of, once it would come out, it would all kind of do that. Okay, well, so that's fine and dandy. But you might remember, or might have done this when you were a kid, if you had a hose or anything, again, anything else, but let's just talk about it like a hose. And let's say that you wanted to take this, and rather than just have the water kind of, just kind of funnel out of the hose as it might normally, what would you do? Well, if you wanted to get the water to come out faster, kind of spray out, what you might do is you might take and you might put your finger over the end of it. So let's imagine I've got this poorly drawn finger. So I take my finger and I block half of the end of the tube. Okay? And I know from experience that when I do this, the water is going to shoot out a lot faster, right? That's just what you actually observe. And so what happens, the reason for that is now this fluid that's flowing, now it all has to kind of come, and it has to come out just this part, this sort of part right here that's open. Right? Because it's only half of the nozzle that's open for the fluid to come out. And when it does, what you see is now this fluid comes out and it goes a lot faster. right? And so this might be something if you've ever washed a car and you were using a hose and you didn't have a specific sprayer, right? You might put your finger over it and you see that the water comes out a little faster and you're able to kind of wash the car with more vigor, whatever it is. But the point is that if you want that water to come out of the hose faster, you block half of the spout or half of the nozzle and you get the water to come out faster. All right, and so hopefully this is something that you've seen before and experienced. But if it's not, you could go and try it with any sort of hose, or even if you had say you had a shower where it all came out as one, all the water comes out of the shower as one big kind of fluid flow. If you put your hand over half of the shower, what you should see is that that the water that comes out of the half that's unblocked, it'll probably come out a lot faster. Okay? And so this is actually going to be an effect that, while we might have seen it in everyday life, it's going to be something that's going to be really, really helpful for us in understanding fluids, and it's going to be a key aspect of them. The whole point here is that because our fluid is incompressible, that means that if we've got the same amount of fluid that is flowing, if we've got the same amount of fluid flowing through our garden hose, and if the end is blocked, that means that we've got to get more fluid through the opening here faster. We've got the same amount of fluid that's approaching the opening, but if the opening is smaller, that means it's got to get through there faster. All right, and so what this means is that if the area through which the fluid can flow is smaller, it's going to go through faster. All right, and again, hopefully that's something that you've experienced, but maybe it's not. But you might go and try it. I think you could find a situation. And so we quantify this. First of all, we quantify the flow rate by this equation, V times A, where V is really the speed of the fluid, and A is the area. Oh my Lanta. It is the cross-sectional area of the hose or the pipe or whatever it is. Okay, so now the idea here is that since our fluid isn't compressible, it doesn't matter whether the fluid is blocked, it doesn't matter whether the nozzle is blocked or not. You've got the same flow rate. That is, you've got the same volume of water that is approaching the end of the hose at all times, whether the end of the hose is blocked or not. And so you've got the same flow rate, but what's different is when the nozzle is blocked versus not blocked is the area. And so if you've got the same flow rate, then that means that Q when it's blocked equals Q when it's unblocked. Okay? And so putting this into, using this with our expression here, what this means is V when it's blocked times A when it's blocked must equal the speed when it's unblocked times the area when it's unblocked. Okay? And so we can see that, we can actually see that, we can rearrange and say, all right, what is the speed of the water when it's unblocked? Well, it's going to be the area when it's blocked divided by the area when it's unblocked times the speed when it's blocked. Or let me rearrange that and make it a little bit better. Let's solve for what is the speed of the water when it's coming out of the hose, when the half of the hose has been blocked. It's going to be the, I guess it would be the area of the hose when it's unblocked divided by the area when it's blocked times the speed the water comes out when it's unblocked. And so what this is saying, the area when the hose is unblocked, when there's no finger over it, is larger than the area when it's blocked, when there is a finger. So this number must be larger than 1. And so that means that if you take a number that's larger than 1, you multiply it by the speed that the water comes out when the hose is not blocked. So now you've got that speed. You multiply it by a number that's larger than 1, and that means that the speed of the water when it comes out, when the speed of the water that comes out of the blocked hose is going to be larger than the speed of the water that comes out when it's unblocked. Okay? And so hopefully that matches something you've seen, but if not, you might try something to play around with it. And this we quantify in a more general equation where we would say for any 2 points in the pipe or a hose or anything, points 1 and points 2, this is a general equation that we'll use. And this we call the continuity equation. And it says that if you've got a pipe and you've got 2 points, 1 and 2, the speed multiplied by the cross-sectional area of the pipe is the same. That quantity is the same for those 2 points. Now, it might be that in some areas, some spots along the way, that the area is smaller. That means the speed is higher, and vice versa. It might be that there are some points along the way where the area is larger, and thus the speed would be lower. So let's just take this. Let's imagine we've got this funny-looking pipe like this. All right, so this is a pipe, and this is water. This is water flowing through. All right, and so let's imagine the pipe has got a large diameter, and then there's a constriction in the pipe, and then a larger diameter again. What this continuity equation tells us is that through here, when it's got a larger diameter which the water can travel through, it's going to travel at a low speed. But at this point where it's blocked, or it's got a more constricted, smaller diameter, the water is going to travel through at a high speed. All right, and then over here it's back to a low speed. Okay, and so this is something that we're going to make use of quite a bit when we're working on problems and analyzing different situations. But for now, that's kind of where I want to leave this video, and we'll build off of this in a following video.